Welcome to The Debate. Today, we're diving into, well, one of the universe's most profound and persistent enigmas, dark matter. This mysterious substance is believed to make up something like, 85% of all matter, yet we can't directly see it, can't really interact with it easily. So scientists are, naturally, relentlessly searching for answers, exploring many hypotheses beyond just the standard dark matter particle idea. Our central question for discussion today is really this: whether the superfluid dark matter hypothesis, which was put forth by Justin Cowrie and Lasha Bergiani in 2015, should be understood as a truly distinct theoretical framework, or if it's perhaps more appropriately viewed as a specific manifestation, a particular state, if you will, within Jay Alfred's broader dark plasma theory, which, interestingly, was published a decade earlier, back in 2005. So I'll be arguing for the encompassing nature of Jay Alfred's dark plasma theory, suggesting it provides a kind of foundational understanding that already houses the superfluid concept.
And I'll be taking the position that superfluid dark matter, the 2015 hypothesis, really is a distinct and, I think, incredibly valuable perspective. It's carved out its own unique space in how we try to understand the cosmos, and I think that distinction, whether it's, ultimately part of a larger whole or truly stands alone, is absolutely crucial for how we approach future research in this area.
Right, absolutely. So let's start maybe by looking at Jay Alfred's dark plasma theory from 2005. Which, as I see it, offers a really robust and comprehensive framework. Alfred's basic premise is that dark matter exists generally as an inert, sort of low-energy dark plasma. But here's the key bit. Near ordinary matter, say within galaxies, it becomes what he termed a dark complex plasma. Now, what makes complex plasma so compelling, I think, is its remarkable versatility. It can behave like a liquid crystal, which basically means it can show characteristics of a solid, a supersolid, a fluid, and, most relevant for us today, even a superfluid, depending on the specific conditions. This inherent flexibility is, well, in my view, a really foundational strength of the theory. You even have researchers like Christian Spethman and his colleagues noting in their simulations, and I quote, "Dark plasma is an intriguing form of self-interacting dark matter with an effective fluid-like behavior, which is well motivated by various theoretical particle physics models." So this fluid-like behavior observed right there within dark plasma, it naturally sets the stage for thinking about superfluidity. Furthermore, we often study plasma dynamics using something called magnetohydrodynamics, or MHD. It basically treats plasma as an electrically conducting fluid. And interestingly, this same approach is also applied to superfluids that are made of charged particles, something often characterized as superconductivity. Jay Alfred himself, back in his 2005 work, actually pointed out the striking similarity between ideal MHD, that's where plasmas are treated as having basically zero electrical resistance, and the phenomena of superconductivity and superfluidity that we see in things like Bose-Einstein condensates. Now, when we consider the quantum properties of superfluid theory, well, we find echoes of them in concepts like supersymmetric Q-balls within this dark, complex plasma idea. You can sort of picture these Q-balls as stable, non-topological solitons, almost like self-contained, stable little blobs of quantum field energy. There are computer simulations by Tumas Multum and the Irovillia that have shown these Q-balls forming from a condensate, and research from CERN by Levine and Shaposhnikov even demonstrated that these Q-balls can actually exist at, well, any temperature, which really broadens the potential conditions under which we might expect to find superfluid-like behavior in plasma, aligning quite nicely, I think, with Alfred's broader theory.
Okay, I do understand the compelling parallels you're drawing there with Jay Alfred's 2005 work, and it's certainly an interesting conceptual space he laid out. However, the superfluid dark matter hypothesis, the one developed by Justin Cowrie and Lasha Bergiani a decade later, in 2015, It really offers a much more specific and, I would argue, impactful alternative. It has distinct mechanisms. Its core idea is, well, quite elegant actually. It proposes that axion-like dark matter particles, you can think of them as very light, very elusive particles, act as a normal sort of liquid outside galaxies. But then crucially, as they cool down in the central regions of galaxy halos, they condense into a superfluid state, specifically a Bose-Einstein condensate. So to put that maybe more simply, just imagine a state of matter where all the particles essentially start behaving as one single, giant quantum wave, moving without any friction at all. Now, the unique consequence of this condensation, according to the theory, is that this dark matter superfluid then generates acoustic waves. These are carried by quasi-particles called phonons. You can think of them almost like tiny packets of sound energy or vibrations propagating within the superfluid itself. These phonons then interact with ordinary matter and mediate a completely new long-range force, one that operates alongside gravity, not replacing it. The real strength of this 2015 theory, I think, lies in its ability to combine aspects of the standard cold dark matter hypothesis with aspects of modified Newtonian dynamics, or MOND. This combination leads to surprisingly good calibration with astronomical observations. It achieves this by treating dark matter as a superfluid within galaxies, which helps explain things like those puzzling flat galaxy rotation curves, and then treating it as a normal fluid out in galaxy clusters, which aligns better with standard dark matter models in those larger environments. It's a very specific and importantly testable framework designed to address precise astrophysical anomalies. Now look, it's absolutely true, as people like Sabine Hussenfelder and others have pointed out, that this hypothesis isn't without its challenges. Significant ones, actually. There's still a lack of complete equations to fully back up the theory rigorously, and we have these pretty big unresolved questions about the specific kinds of particles that could form this superfluid and exactly how a fluid manages to condense into a superfluid state within the highly complex, curved space-time environment of an actual galaxy. These aren't just minor details, right? They are fundamental unknowns. And they really highlight, for me, the hypothesis's distinct nature and its ongoing need for focused, independent development rather than just being, sort of folded into a broader, pre-existing theory.
That's an interesting and detailed outline of the Corey-Bertigiani model's specificity. And I can certainly appreciate the elegance of its proposed mechanisms with the phonons and such. However, I still come back to the idea that Jay Alfred's 2005 dark plasma theory offers a far more, let's say, encompassing framework. Where I guess we diverge is that I don't necessarily see that versatility you mentioned as a weakness. I actually see it as a strength. It's a theory that seems capable of explaining various states and behaviors of dark matter, and the specific superfluid state that you're describing, with its liquid and crystalline characteristics, it seems to fit quite naturally as just one component, one particular phase transition within the broader dark plasma theory that Alfred outlined. His conceptualization of dark complex plasma, having this ability to exhibit these liquid crystal properties, and by extension, superfluid-like behavior, it really demonstrates its fundamental capacity to host such phenomena. The Corey-Bertigiani superfluid, viewed in this light, could just be a specialized instance, a particular realization of dark matter's behavior within a larger, more general system that Jay Alfred described years earlier.
I understand your argument for a broader umbrella, but I'm not quite convinced that simply having a general framework is sufficient here. While Jay Alfred's dark plasma theory provides, yes, a robust descriptive framework, the superfluid dark matter hypothesis from 2015 provides a precise and testable mechanism. It has specific proposed particles, those axion-like particles we talked about, and specific interactions, crucially through those phonons. This gives us a clear pathway, something concrete, to address particular gravitational anomalies like those galactic rotation curves that the standard cold dark matter model still really struggles with. The broader claims of dark plasma theory, while certainly intriguing, might lack that kind of focused, testable detail needed for explaining these very precise phenomena. The 2015 hypothesis introduces a novel force through phonons interacting with ordinary matter.
That's a significant addition, something that Alfred's 2005 theory didn't explicitly detail in quite the same way, did it?
And honestly, I do question whether Alfred's 2005 theory adds anything truly new in its explanatory power beyond what the standard dark matter hypothesis already covers in some regimes. Especially, like I mentioned, in regions such as galaxy clusters where the superfluid dark matter model itself behaves essentially as a normal fluid, yielding results consistent with the standard model anyway. It really seems the superfluid theory specifically targets areas where the standard model falls short, and it does so with a distinct new mechanism involving this extra force. Does Alfred's original work from 2005 offer that same kind of specific new explanatory power for these particular stubborn anomalies?
Okay, that's a fair challenge regarding the novel explanatory power for specific anomalies. But I would argue that Jay Alfred's 2005 dark plasma theory actually did note key features that are common to the later superfluid theory, demonstrating, I think, a remarkable prescience and effectively laying the groundwork for exactly the kind of mechanisms you're describing. For instance, the generation of acoustic waves, what plasma physicists call Alphen waves, in plasma that's immersed in magnetic fields. That's a well-established phenomenon, and Alfred discussed this connection. These are essentially sound-like waves propagating through a conducting fluid, which is conceptually, at least, very similar to the phonons carrying acoustic waves in a superfluid. Furthermore, plasma is, well, it's known for having long-range correlations. That means particles within it influence each other over pretty large distances, creating a kind of interconnectedness across the medium. In fact, this is often considered a defining feature of plasma, much like the interconnectedness the superfluid theory stresses for the state within galactic centers. And consider vortices. Corey notes that when a superfluid is spun faster than some critical velocity, it develops these quantum vortex lines. He suggests the typical angular velocity of galaxy halos could potentially give rise to an array of these dark mattered vortices. Well, these vortices are actually well known, extensively studied signature features of plasma when it's in a liquid state. They arise quite naturally from magnetohydrodynamics. So these parallels between Alfred's initial descriptions of plasma behavior back in 2005 and the concepts highlighted in the later superfluid theory, well, they don't seem like mere coincidences to me. They suggest a fundamental underlying connection. And moreover, this notion that Bose-Einstein condensation, which is obviously crucial for superfluidity, requires extremely low, near absolute zero temperatures. That's a common assumption, right? But it's been significantly challenged. Research by Alexander Serga and his team back in 2014, for example, concluded it doesn't necessarily require those ultra-low temperatures. Other studies suggest Bose-Einstein condensation might even occur in relativistic plasma at billions of Kelvin, perhaps like conditions within neutron stars or even in the quark gluon plasma thought to exist immediately after the Big Bang. This body of research indicates that superfluid plasma could potentially exist even at incredibly high temperatures and in very diverse cosmic environments. This strongly supports, I think, Jay Alfred's original view of dark plasma, having the potential to transition to a superfluid state under a much wider range of conditions than perhaps initially thought, making the Hori-Bergiani model look like a plausible specific case within a broader existing framework he described.
That's a compelling point regarding the conditions for Bose-Einstein condensation, and the parallels you've drawn are certainly interesting. However, we really must return to the very fundamental theoretical and observational hurdles that are facing the superfluid dark matter hypothesis itself. The ones I mentioned earlier, drawing on concerns raised by, for example, Sabine Hossenfelder. They aren't easily dismissed. I think the biggest problem, maybe, for the Hori-Bergiani model right now is the lack of clarity on what specific types of dark matter particles could even form this superfluid state. And critically, how does this condensation actually occur in the incredibly complex, highly curved space-time environment that governs galaxy formation and evolution? These are not just, trivial details that can be simply hand-waved away by pointing to a broader plasma theory. Most superfluid studies we have are conducted in labs, here on Earth, under very specific, highly controlled conditions. Extrapolating that behavior to the vast, gravitationally warped expanse of an entire galaxy, especially without a complete understanding of the underlying particle physics involved and the exact condensation mechanisms for dark matter specifically, well, it makes the 2015 superfluid dark matter hypothesis a very distinct challenge. It requires independent theoretical development. Simply stating that plasma can be superfluid doesn't really resolve these core ambiguities inherent in the Corey-Berreziani model when you try to apply it to the unique and frankly largely unknown nature of dark matter within actual galactic environments. It's potentially a very different beast than, say, superfluid helium in a laboratory dewar.
Right? I absolutely hear your concerns about the specific mechanisms of condensation in galactic curved spacetime. And yes, they are indeed significant hurdles, no doubt. However, the, let's say, robust theoretical foundation for plasma's general fluid-like behaviors and its potential for superfluidity, even under extreme cosmic conditions, I think it strengthens the fundamental plausibility of Jay Alfred's 2005 conceptualization of dark plasma acting as a superfluid. We do have examples from ordinary matter physics that shows superfluid states aren't exclusive to these exotic, ultra-cold lab settings. Think about transient superfluid plasma observed in liquid helium experiments, or the theoretical proposals for Bose-Einstein condensates in relativistic plasma at billions of Kelvin, or even within neutron stars. Physicist Tigran Kalajanyan, for instance, considers the quark-gluon plasma right after the Big Bang to have potentially been a superfluid. So these examples, they illustrate that superfluid states can arise in diverse, energetic cosmic environments. This broader evidence for plasma's inherent ability to exhibit superfluidity, which Jay Alfred highlighted the potential for back in 2005, it provides, in my view, a strong conceptual umbrella under which the Corey-Berreziani model could logically find its place. Even if the specific dark matter particle and the exact condensation details remain, big question marks and need to be fully elucidated, the phenomenon itself, the idea of dark matter's superfluidity, seems like it could be a natural and perhaps even anticipated extension of dark plasma behavior as Alfred described it.
I absolutely acknowledge the existence of superfluid phenomena in these incredibly diverse and extreme settings you detailed. That's well established. However, my core point remains that the 2015 superfluid dark matter hypothesis specifically grapples with how dark matter particles which, let's be honest, we barely understand at all, would behave and condense in curved spacetime on galactic scales. The challenges that Sabine Hossenfelder and others have noted aren't just about generally how fluids condense. They're about how this particular fluid made of unknown dark matter particles condenses into a superfluid state within the unique environment of galaxies. The lack of understanding regarding the specific types of dark matter particles that could form the superfluid and the actual mechanics of condensation in the presence of strong, dynamic gravitational fields, these are unique problems tied directly to this hypothesis. They are not merely, I think, implementation details to be filled in later by referring to a broader, more general plasma theory. These are fundamental unknowns, and they strongly suggest, to me at least, that the superfluid dark matter hypothesis requires continued, distinct development and significant theoretical refinement to truly stand on its own 2 feet, rather than simply being subsumed right now as just one possible state within Jay Alfred's earlier, more generalized dark plasma theory. Perhaps integration can happen later, absolutely, as our understanding evolves, but the foundational work needed for superfluid dark matter feels, for now, quite distinct.
Okay, so as we bring our discussion towards a close, I still maintain that Jay Alfred's 2005 dark plasma theory presents a compelling and remarkably comprehensive framework. It seems to offer a foundational understanding of dark matter as this versatile plasma state, one that appears capable of encompassing many of the intriguing features that were later explored in more detail by specific models like Corey and Berreziani superfluid dark matter. The parallels we discussed in concepts like acoustic waves, long-range correlations, vortices, coupled with the proven potential for superfluidity under various conditions, they really suggest a deep underlying connection where Alfred's earlier work provides the broader canvas, so to speak.
And while I acknowledge there are undeniable affinities, yes, and overlaps in these concepts, I still hold that the 2015 superfluid dark matter hypothesis offers a truly distinct and valuable approach. Its particular strength lies, I believe, in its specific mechanisms for interacting with ordinary matter, namely through those phonons, and its unique synthesis of existing gravitational models, combining elements of MOND and standard dark matter. the very specific challenges it currently faces, the crucial need to identify the constituent particles and fully understand condensation in curved spacetime, actually underscore its independent trajectory in trying to address very particular gravitational anomalies that seem to demand focused and perhaps novel solutions.
Well, ultimately, I think both of these perspectives really highlight the incredibly intricate and constantly evolving nature of dark matter research. It's an area of physics that continues to fundamentally challenge our understanding of the universe.
Absolutely. And this kind of rigorous intellectual exchange, even when we're discussing theories that clearly have significant overlaps and similarities, is just crucial, isn't it, for exploring these complex phenomena and hopefully pushing the boundaries of our knowledge forward?
Agreed. And further observational data, plus continued theoretical refinement on all fronts, will undoubtedly be essential in distinguishing between these ideas, perhaps integrating them, or maybe even further developing these fascinating perspectives on the universe's unseen components.
Indeed. So much more to explore here.
We certainly hope that by considering these different perspectives today, even though they share common ground, you've perhaps gained a deeper appreciation for the ongoing quest to understand the universe's most profound mysteries. Thank you for joining the debate.